Hello and welcome to our video on reactions involving alcohols. Today we'll be going over some of the differences between primary, secondary and tertiary alcohols, and then going over some of the reactions that alcohols are involved in. So firstly, it's important to delineate between a primary, a secondary and a tertiary alcohol. So with the primary alcohol, it has a central carbon and with only one alkyl group, so that's signified by R there, R1. With the secondary alcohol, it has, instead of two hydrogens, as in the primary alcohol, it has two alkyl groups, so R1 and R2. And in the tertiary alcohol, it's all alkyl groups. It doesn't have any hydrogens bonded. And this will influence some of the reactions that each of the alcohols can be involved in, especially oxidation reactions. So like alkanes and alkenes, alcohols can also undergo combustion reactions. You have the complete version in the form of in the presence of high amounts of oxygen, and the incomplete version in the presence of low amounts of oxygen. The complete version will, as you know, form carbon dioxide and water, and the incomplete version will form carbon monoxide, or could form just carbon and water. So the first kind of reaction we have is the dehydration of alcohols. Alcohols can undergo a dehydration reaction to produce their corresponding alkenes. You need two things for this type of reaction to occur. You need a concentrated sulfuric acid catalyst, so it needs to proceed in concentrated sulfuric acid, and you require quite a high temperature and you don't need to memorize these temperatures, just know that it's highest for the primary alcohol, and as you go along to the tertiary alcohol, it decreases in temperature. So it's also important to remember that wherever the OH group is present, the double bond is made between those two carbons. So we have a simple example, ethanol, with I'm going to say concentrated sulfuric acid, and that'll proceed to form ethene and water. So that's the most important thing. But I'll show you another example. So if I were to have an alcohol that looks like this, and say the OH group was in this position. So this would be butanol. If I were to form the dehydration reaction, so essentially what would happen is I would get rid of this bond here, obviously, and I would have a double bond in this position. Just remember, you have the double bond in between the carbon and the carbon before. Another important reaction to remember is that alcohols can actually act as weak acids in the form of sodium. This is really similar to the reaction that water undergoes when it's put into sodium. So essentially, alcohols react with sodium to form an alkoxide, which is the alkoxide anion, which is the alcohol, but instead of an OH, it just has the O-, which is the most important thing, and it also forms hydrogen gas. It's important to note that this, as I said, the alcohol actually acts as a weak acid, and thus the alkoxide is a really strong base because it's the conjugate of a weak acid. If you want to revise that, go back to our videos on pH. So if the alkoxide is a strong base, that means the alcohol is a weak acid, and vice versa. So I've got this is the general formula for the reaction, but on the bottom I've represented that with ethanol reacting with 2Na gives you the alkoxide and the hydrogen gas. It's also important to know that when you chuck this alkoxide back into water, or you make it react with water, this alkoxide will generate the original alcohol and also an OH- anion. So oxidation is a pretty important reaction that alcohols can undergo. You usually need a pretty powerful oxidizing agent such as chromic acid for these reactions to proceed. And we'll go over an worked example to show you how this actually happens. You don't actually need to memorize this schema. It's just mainly for your understanding. So here we have a secondary alcohol that I've just concocted. So essentially the OH group and the OH group present in the chromium acid. So basically the OH group in the alcohol and the OH group in the chromic acid will kind of combine and gel together and react. So you have two OH groups. So you get one product, which is an O bond, so a carbon-oxygen bond, binding the chromic acid and the alcohol, and you also get water as a byproduct. So, and that's kind of what happens. So the OH and H kind of react to give you the water, and the O is left behind, and that's what gives you the bond. And that's kind of what happens. So you have the alcohol directly bonding with the chromic acid to form this intermediate. So, well, now that you've understood that, this water that we've ejected, or the water molecules that are floating around, it's important to understand that they have two lone pairs of electrons. So they can actually form a coordinate covalent bond, and this hydrogen is actually quite attracted to them. So they can actually form a coordinate covalent bond with this water, and I'll show you that schematically. So now you have H3O plus, so I'll get rid of this. So now you have this pair of electrons. It's also important to understand that this CO bond that's bonding the original alcohol to the chromic acid isn't entirely that stable. So what will happen is these two electrons will start to contribute to this bond. So you now have a double bond forming. And this is stable enough, so this byproduct will kind of eject, if that makes sense. So you get three things. You get the ketone that we made, which is this group here. The left of the chromic acid, which I'll show you schematically, which is this, and then you have the H3O plus. So in this way, alcohols can be oxidized with chromic acid. So before we begin our conversation on the specifics in regards to oxidation reactions and the different types of alcohols, it's important to set up some context surrounding oxidation states as well as what oxidation reactions actually are. So please refer to our original video on introductions to organic reactions to see oxidation reactions and what they are in a bit more detail. But simply put, when a carbon in an organic compound loses a bond to a hydrogen and gains a new bond to an oxygen, that's what we classify as an oxidation reaction. So that's an alcohol turning into an aldehyde or a ketone, and I'll show you some examples and put this into practice in the next couple of slides. But we'll have a quick chat on oxidation states. So there are three rules you need to remember with an oxidation state. So a carbon-carbon bond does not affect the oxidation state at all. So it has a +0 contribution. A carbon-hydrogen bond will decrease the oxidation state by -1. A carbon, I've put the letter Z, so a carbon Z compound or carbon Z bond will increase the oxidation state by +1, and Z could be any electronegative substance such as the freaks of nature or sulfur or any halogen for that matter. And please also remember that the freaks of nature are fluorine, oxygen, or nitrogen, and they're the three most electronegative compounds. And then that will give you an increase in the oxidation state by +1. And I'll give you a quick example. I'll just draw one down the bottom. So here I have methane gas, and I'll give you a brief moment to calculate the oxidation state. That would be -4. And I'll give you another example, which would be so this one's a little trickier. So we have -1 for the carbon-hydrogen bond, -1 for the carbon-hydrogen bond, -1 for the carbon-hydrogen bond, but then we have a +1 here for the carbon-oxygen bond, giving you a grand total of -2. So primary alcohols will either oxidize to form a aldehyde or a carboxylic acid depending on the circumstances. So simply put, as I stated previously, when a carbon atom in an organic compound loses a bond to its hydrogen and gains a new bond to an oxygen, then it's been oxidized, right? And we can see that in full effect. So say we have this carbon-hydrogen bond here. It's an oxidation reaction as we lose one of the carbon-hydrogen bonds. So in the alcohol, we have two carbon-hydrogen bonds. In the aldehyde, we only have one. One of those carbon-hydrogen bonds has been used to form the double bond with the oxygen. Now, if we oxidize that again, we lose another carbon-hydrogen bond. So in this carboxylic acid, we have 0 carbon-hydrogen bonds. And what that carbon-hydrogen bond has been used to form this OH group. So there's a couple of circumstances we need to go over, and before that, I'll show you exactly why primary alcohols will form an aldehyde or a carboxylic acid. And especially, I think this step is important to go over, why they form the aldehyde. So with the primary alcohol, we can actually revisit this reaction and understand why they would form an aldehyde as opposed to anything else. So with the water molecule, in this alcohol, it's actually got one extra hydrogen because it's a primary alcohol. So when the water comes along and kind of rips off this hydrogen, there's one remaining. And I'll show you the latter part of this reaction. So we still have two electrons present in this double bond, which go on to form this double bond here. So overall, when we form it, we get this byproduct here, except this time we have a hydrogen, and that by definition is an aldehyde because you have a double bond oxygen and alcohol group and a hydrogen. Now, I said that the primary alcohol could go on to form either the aldehyde or the carboxylic acid. Think of it as a continuum. So this is like the first step in the reaction, and this is the second step. If you use a weak oxidizing agent such as a DMP, for example, only the first step can be complete. So if you react the primary alcohol with DMP, you would only produce the aldehyde. However, if you use, and I'll put that in black here. However, if you use something stronger, so maybe like a chromium acid, for example, which is a very strong oxidizing agent, it will actually undergo the first step and then the second step. So the reaction will, if you like, proceed to completion, and then you'll get the carboxylic acid at the very end. So with the secondary alcohols, they will always oxidize to form ketones, and we can refer back to our initial explanation on the oxidation of alcohols to see why. So unlike the primary alcohol, where there was a hydrogen, in the secondary alcohol, there will be no hydrogen. So there will be two alcohol groups, and I'll show that with R1 and R2. So the same thing happens. The water comes along, rips off this hydrogen, this bond creates a double bond here with the oxygen. However, this time you have no hydrogen. You have an R1 and an R2, so two alcohol groups and a carbon double bond O, and that by definition is a ketone. So the only thing the oxidation of a secondary alcohol can perform or form is a ketone. Last but not least, we have a tertiary alcohol, so a carbon-based alcohol with three alcohol groups and no hydrogens, and these do not readily or at all undergo any oxidation, and I'll show you why that's the case. So with the oxidation of alcohols, especially with a reagent such as chromic acid, this kind of step is very integral. So this step where the water comes in and kind of rips off this hydrogen here. However, with the tertiary alcohol, it doesn't actually have any hydrogen to rip off. It has, instead of this, it has R1, so alcohol group 1, alcohol group 2, alcohol group 3. The water can't just come off and rip off the alcohol group, so thus these reactions do not proceed to completion. Last but not least, alcohols can also undergo esterification when combined with carboxylic acids in the right circumstances. However, we will be covering this reaction in the video involving reactions in carboxylic acids.